So we turn now to a quantitative description of Brownian motion and illustrate the use of the Langevin equation. So this is an equation for a system subject to random fluctuations. It's basically Newton's second law that says the sum of the forces on a particle is equal to its mass times its acceleration. And those forces are the damping, if the particle's moving at a velocity given by x dot, the on the slide, plus some random forces acting on the particle. In the case of a spherical particle immersed in a viscous liquid, alpha would be the Stokes law damping coefficient, where a is the radius of the particle. So let's elaborate on this term here, the random force. Since it's random, the thermal average of this force will be zero. A second condition that we impose is that this force acts only as an impulsive force to push the particle, and so that the correlation of this force over time, thermally averaged, that is the product of the force times the force at some time t prime, is just a delta function in t minus t prime. So the force is finite only over a period of an effective collision. So to go ahead and solve this equation, we need to change variables, and it's convenient to set up the equation in terms of this compound variable x dot, and we can do that by multiplying the whole equation by x. One other trick we have done here is to write out then the mass times the acceleration times x dot in the following way. And the reason for that is that the time derivative of x dot is x dot squared plus x double dot. So the result is then proved. So with this equation in this form, we take a second step, which is to thermally average the quantity x dot. When we do that, two things happen when we take the thermal average of every term. First of all, the force thermally averages to zero, so we can drop the term in the random force. The second thing is that this term mx dot squared can be derived from the equipartition theorem, because a half mx dot squared is a half kt. So with this then, the equation reduces to this much simpler form shown at the bottom of this slide. So now we have to solve this equation. It's an equation that says the time derivative of the variable is some constant plus another constant times the variable itself, and we know that the solution to equations like that is an exponential. So we can then write this down. By looking at the, substituting this into the equation of motion, taking the derivatives, and then setting t equal to 0, so the exponentials now become unity, we obtain straight away that c is kt over alpha. We obtain b similarly because we require the coefficients of the exponentials to be identical on the left and right hand side, and so from the same equation we obtain b equals minus alpha over m. Obtaining a is a little more tricky. What we do to obtain a is to re-express x dot as 1/2 of d by dt of the thermal average of x squared. You'll see by substitution that this is correct because you get 2x dot from taking this derivative. And then we look at this equation subject to the boundary condition that x is 0 at t equals 0. And when we do that, we obtain the result that a is minus kt on alpha. So with all of those results combined, we now arrive at a second differential equation, but one in which the variable is now x squared thermally averaged. And here it is. It says that d by dt of x squared thermally averaged is 2 kt on alpha times 1 minus e to the minus alpha t on m. We can solve these with another substitution shown on the slide, and subject to the boundary condition again that the mean square movement of the particle at t equals 0 is 0. We end up then finally with the following equation for the variable x squared thermally averaged. This is a complicated looking equation, but if we take the limit where the time is greater than m over alpha, we can drop the exponential term and we end up with a very simple result shown on the next slide, which is that the thermal average of x squared is given by 2 kt over alpha times t. Remember that alpha is 6 pi a eta. This tells us that the root mean square, so we take the square root of both sides of the equation, displacement of the particle is proportional to the square root of time, a result that is in stark contrast to the motion of a particle subject to no force at all, in which case the velocity is constant and the displacement increases linearly with time. Now you see from this solution here, let's just write this out, and we're going to use this value for alpha, that the coefficient that appears in front of time goes like 1 over the square root of the 1 over the viscosity, 1 over the square root of the viscosity if we consider the mean square displacement. And so this panel here shows polystyrene latex particles in water, and here in a solution of DNA where the viscosity is higher, and you can clearly see without even any analysis of the slides that the root mean square fluctuations of the particles are much smaller in the more viscous medium.